move on to our next speaker, who is also our co-chair, Dr. Jeffrey Gillis-Davis, and his title is Analyzing Dual Laser Space Weathering Effects.
Okay, I'm trying to share. Mike, it still says host disabled participant sharing screen for me.
Interesting. Are you sharing? Sorry, that's my bad. Do you have a second account on that I can? Oh, that's probably why. Okay.
Yeah.
Okay, try now.
Okay. All right, so a little shift in things. We're going to move on from ions to micrometeorite bombardment of space weathering. And this is work that I'm doing as part of our survey ICE 5.0 with collaborations from University of Hawaii and San Francisco State. So I'm going to talk about, I'm actually just using long pulse laser space weathering method to make agglutinants. Okay. All right, so in the sense of lunar space weathering, we have a number of different parameters to try and recreate with laser space weathering, and I've outlined 5 of them here. The first is rims that occur on minerals, and those rims, in this case an inclusion-rich rim, often have nanophase iron in them. And with short pulse lasers, we can recreate that feature. Another very common feature in lunar regolith are the agglutinates, which in a mature lunar regolith can comprise up to about 60% modally of the regolith. And with the short pulse only laser, we cannot produce these agglutinates. And by the lack of producing these agglutinates, we also don't make a lot of nanophase iron and the microphase iron. And this feeds into the magnetic signature that was measured by Morris in his 76, 78, and 80s paper, where it became a maturity index where the I sub S normalized to the FEO matches and is used for maturity parameters. But in measuring I sub S of FEO of our short pulse laser space weathered regolith, we don't get very high in I sub S or FEO. We only get about 10 or 14, which is very immature. So we don't replicate that feature very well. In the case of Spectra, we do that pretty well. Here on the plot in the lower left, you'll see there's 3 Spectra. One is of a rock, the dotted line. And you can see that for a lunar, in this case a Mare rock, we have a very good absorption band at 1 and 2 microns showing pyroxene. But as we look at a soil that has been naturally space weathered on the surface of the moon, but is of similar composition, the black line there, you can see that those mafic absorption bands have now just essentially almost disappeared. The spectrum is darker, it's lower down. And if we normalize that spectrum at 500 nanometers or 0.5 microns, which is the line with the dots, you can see that the spectrum is also redder than the typical fresh rock material. In other words, it increases in reflectance as it increases in wavelength, and these are all key features in lunar space weathering. And the short pulse laser reproduces some of the darkening, definitely the redding, and a little bit of the loss of the spectral absorption, but doesn't completely or nearly erase them like we see on the moon. And then on the lower right, there's XRD analysis by a paper by Taylor et al. In 2019, which minerals show good peaks that are related to elements and elements in different mineral lattices. And for lunar regolith, where there is a lot of agglutinates, there's this amorphous hump that you can see on the very low part. It doesn't have Bragg scattering because it's just elements in a glass. So it's another criteria which we need to be able to recreate with laser space weathering, but we don't. So our motivation was to add a second laser. So typical lunar space weathering, we use the short pulse, as I mentioned before, which is a 10 nanosecond pulse length. That's about 30 millijoules per pulse. And this creates a lot of vapor and makes rims on materials. But what we've added is a longer pulse, 100 nanosecond pulse, higher energy at 300 millijoules per pulse. This creates more of the melt deposits and makes agglutinates. So on the image below that, you'll see there's two lasers. The blue one is the short pulse. It goes through a beam splitter and then into the chamber. The other laser, it bounces off and gets combined with that pulse. So we're hitting the sample at the same time. The laser energy then is directed or redirected in the top images down into a vacuum chamber. So our experiments are done under vacuum. And we also use loose powders to more faithfully replicate a lunar surface. And that actuated mirror actually steers the beam in X and Y, and the lunar plasma actually gardens the sample. With each shot, it creates little craters. And in the future, those open circles, we're going to be adding temperature controls as well as the addition of volatile species. So as I mentioned before, the spectra that we see, so on the left is spectra of San Carlos olivine that we have laser weathered with the short pulse spectra. You can see very top, you have a nice 1 micron absorption, and then after about 40 minutes, it becomes what we call spectrally mature. It doesn't change much, even if we add more laser radiation. You can see the spectrum is red. The 1 micron feature is still somewhat present, and it has darkened. On the right is our long pulse spectra. Again, this is San Carlos olivine, and as you can see, as we move in lower albedo, our longer duration of long pulse, at 32 minutes, we have made a spectrally mature material that the 1 micron band is essentially erased. It is definitely flatter, or what we call bluer, than the short pulse laser weather measurements, and it is definitely a lot darker and more closely matches lunar materials that have been space weathered. And just for a comparison, I just popped up there on the green line, the short pulse lasers. You can kind of compare, where we are at the maximum amount of laser space weathering with short pulse versus the maximum kind of intermediate amount for long pulse weathering. We can take these spectra, and this is work that Heather Kaluna has done for this project, where we do principal component analysis, and we wanted to compare this to real Apollo samples to see how we're faithfully reproducing our weathering. So on the right, on the bottom, we have PC1, which corresponds mostly to albedo, and PC2 on the y-axis, which mostly correlates with the continuum slope. We have Mare Highlands and Apollo 14 samples with the different color codes. The size of the samples correlates with maturity. These are samples that have been taken from the LSCC, and we have the I sub S over FEO. So we're able to correlate spectral parameters here with I sub S over FEO, or maturity. And you can see that they dominantly move from immature to mature. They get darker and they get redder. Now I've popped up these green circles, are results from our short pulse only laser. One takeaway is the immature material from the moon is still, more mature than what we did with the short pulse laser in this scenario. But you can see the trend is roughly what we see, but definitely steeper. We get it a lot more red with our short pulse. Now we'll pop up the long pulse laser. So these circles, the yellow-green circles, are the long pulse laser results. You can see that we are now able and capable to get into the same field in the PCA or PC space for PC1 and PC2 compared to fresh and mature lunar materials, but particularly Mare materials. And this again is also showing with PC3 and PC1, where PC3 here is spectral contrast, so loss of spectral feature. Again, we're seeing that we match Mare material very well. Next are some SEM images that I'll go over really quick. Left is a lunar agglutinate. Right are some laser agglutinates that we've made. They look pretty similar. The far right image just kind of shows we can make them of all different sizes. Viscosity, Acicularity is also a feature that we need to replicate. We do see we create some vesicles. Left is Apollo. The two right images show some vesicles as well as the microphase and nanophase iron kind of zoomed in. Then this is a cross section of the agglutinates as well, showing again different kind of nanophase iron, different structures, complex and simple balls, and the nanophase iron. And then for our conclusions, you know, with the dual laser experiments and only using San Carlos olivine, we are pretty well reproducing things. We're able to form agglutinates, and the big takeaway is that, you know, once we create these under vacuum, we can do other experiments, and we're still waiting to get some TEM and isobes over FeO values for these materials. Thank you.
Yeah, thank you.